Let's say you want to simulate a solar system or something. You could use the velocity of Rayleigh algorithm like we said before, but there are plenty of different ways to solve this problem. Another way is with the forward Euler method. But here's the thing. If you run the two simulations side by side, you might notice at some point in the future that there's a difference between the two of them. And your question might be, which of these two methods is more accurate? Unfortunately, the answer here is rather obvious. The velocity of Rayleigh algorithm is simply more accurate than the forward Euler method. And this begs the question, why would you ever use the forward Euler method if you could instead just use the velocity of Rayleigh algorithm? Truth be told, Euler methods are not used that much in practice. However, Rayleigh integration was meant specifically to solve the kinematic equation. Euler methods introduce a new class of algorithms meant to solve ordinary differential equations and are thus slightly more general than Rayleigh integration. See, Rayleigh integration was meant to solve this problem. But Euler methods can solve any of these and many, many more, so it's clear that Euler methods are way more general than Rayleigh integration. However, Euler methods obviously come with a bunch of problems. Euler methods are rather straightforward. If we want to solve some ordinary differential equation for some variable, let's say x, with some given initial location, all we need to do is say that the next spatial step for x is going to be equal to whatever it was before, plus some small change based on its derivative. For example, with the kinematic equation, if we want to move our simulation forward with time, we simply say that x equals x naught plus v naught t, where v is obviously the time derivative of x. However, this obviously begs the question, what did we do with the acceleration term? Because, as we see it now, this is not the kinematic equation. Well, there are two somewhat okay answers here. The first is that the velocity term inherently has an acceleration term in it, because it is in itself an ordinary differential equation, where the velocity is equal to the velocity of some previous time step plus its derivative times some time step. The second answer is that as long as you keep your time step small enough, you won't really accrue that much error, and that's completely true. As long as you keep your time step small enough, Euler methods work perfectly fine. Let's take a simple case of dy by dx equals x. In this case, if y of 0 equals 0, we know the solution. Y equals x squared over 2. However, if we solve this differential equation with the forward Euler method, depending on which time step we use, we'll get slightly different results. If we use an incredibly coarse or very large time step, then our result from the forward Euler method will be significantly far off the analytical result we expect. As we make our time steps smaller and smaller, we get closer and closer to the result we want, until eventually it converges almost exactly. This is the main problem with Euler methods. If we choose a really large time step, we get incredibly wrong results. In fact, let's take the case of another differential equation. dy by dt equals negative 3y. In this case, the answer is also somewhat obvious. It's e to the negative 3t. But we have a bit of a problem with Euler methods in this case. If we use a large time step, the results are actually unstable. That is to say, they oscillate somewhat wildly, above and below 0, sometimes even going off to positive and negative infinity. And that's definitely not okay. Between this instability and the error that we mentioned before, there really isn't a reason to use the forward Euler method in practice. However, it does introduce a large class of algorithms that we'll be using in the near future. For now, there's a chapter available on the algorithm archive awaiting language-specific implementation. Feel free to go there and implement it in your favorite language. Outside of that, thank you so much for watching, and thanks to these people for contributing to the algorithm archive so far. I see the forward Euler method as a metaphor for life. So long as you take sufficiently small steps forward, you'll be fine. But the moment you want to take a large step forward and change your life for the better, you'll probably make a bunch of errors or become emotionally unstable. Yeah. And on that note, I will see you next time.